Hi, everyone. My name is Melissa Hernandez Alvarez, and I have the honor of introducing our distinguished guest, Emerita Professor Judith Grabiner. Professor Grabiner has been a part of the Pitzer community since 1985. I had the opportunity of being one of her advisees as I am an alum from the class of 2015. And let me tell you, she is a phenomenal woman. Something that struck with me is that Professor Grabiner teaches the history of math and reminds students that math is not simply just numbers and letters. You need the interdisciplinary connections of history, science, and the humanities to fully understand math. Being a woman in mathematics continues to be trailblazing and inspires others like myself to serve as a powerful example that women can be a part of this field. Oh, and in case you didn't know, Professor Grabiner was recently awarded the 2021 Albert Leon Whitman Memorial Prize, which recognizes notable exposition and exceptional scholarship in the history of mathematics. Please join me in welcoming Professor Grabiner today.
Okay, thank you. Thank you very, very much. All right, let's go. All right, can you guys all see this exciting title page? Excellent. I'm going to minimize you. And here we go. I thank you for the introduction. I didn't realize I'd be introduced by a former student. That was kind of cool. This talk has an introduction in two parts. I'm going to start doing that. And when I'm done with the introduction in two parts, then I'm going to do the really fascinating part of it. And then I hope there'll be time for questions. So here goes. Hey. All right, it doesn't. All right, hang on. All right. I'm new at this. All right. So when I first started trying to teach mathematics in different cultures, what people would say to me was, that's nonsense. There isn't any different mathematics in different cultures. 2 and 2 is 4, and that's true for everybody. And yeah, that's true. 2 and 2 is 4 everywhere. But even the way people write numbers is different in different cultures, and there are cultural choices that are made, and I want to show you a little bit of them. I'm going to enable the arrow here. All right, the tally system, the ancient Egyptian is a very good example. 1, 2, 3, 4. You want to add in tally system, it's very easy. Look, 3 plus 2 is 5. That just happens automatically. That's 10, 20 is 2 of these, and so on. Tally system, very nice for adding. Place value system, like the modern Hindu-Arabic system that we use, you recognize these figures. Place value is good for multiplication, because to multiply by 3 million, it's just the same as multiplying by 3. You just add the requisite number of zeros. That's why you have zeros. That's what they're for. Another way of writing numbers is to take your alphabet, the way the Greeks did, or the ancient Hebrews did. The first letter is A, or alpha. The second letter is beta. Okay, so beta means 2, gamma means 3, iota means 10. The next Greek letter is the kappa, that's 20. All right, now this limits how many numbers you can write, but for small numbers, it works really well. And it also gives you a very interesting cultural construct, because every word has a numerical value. If there were a Greek word that was spelled beta gamma, its numerical value would be 5. And so the numerical value of your name, for instance, could have some mystical significance. This is all culture. The Chinese also had base 10 place value system. These are their numerals. I want to call your attention to the 1, the 2, and the 3, just like the Babylonians, but they decided to do it horizontally instead of vertically. All these things are cultural choices. Okay, the way people use numbers is also different in different cultures. And I'll give you a little more advanced example here. Whoops. Yeah, the same math, different versions in different societies. You don't need to know what the Pascal Triangle is, but this is the Pascal Triangle. So here you have it in China. You recognize the Chinese numerals in it. Here you have it in medieval Islam. Pascal used it for probability theory. In China, it was used for expanding binomials and extracting roots. In the Islamic world, it was used for permutations and combinations. So the same math, different reasons. Mathematics also is done by people who are not professional mathematicians. For instance, there's a linguist in India, 2nd century BCE, called Pingala, who analyzes Sanskrit poetry, and he uses the numbers that are later put into the Pascal Triangle to calculate how many combinations of short vowels and long vowels are possible in a line of poetry. For instance, in a 3-syllable line, it can have all long, it can have 2 longs and 1 short. See 3 ways to do that. It can have 2 shorts and 1 long, 3 ways to do that. And it can be all shorts. And you recognize the 1, 3, 3, 1 there in the Pascal Triangle. So in the 10th century, another linguist called Halyuda put those same numbers, which we call the Pascal Triangle, into a triangle. He called it the Meru Prastara. Mount Meru is a sacred mountain in India. Prastara means algorithm or step-by-step procedure. But here's our friend, the 1, 3, 3, 1 again. This is done not by a mathematician, but by a linguist. They call Halyuda a mathematician on the web. That's not right. He's only a mathematician if you consider him a contributor to mathematics, but he was, in fact, a linguist. Priests and rabbis and other religious leaders describe the motion of the moon and the sun using mathematics in order to establish religious calendars in many traditions. This is the Aztec calendar stone. This is a very simplified version of the Jewish calendar. That is Stonehenge. Other mathematics done by religious figures. Religious figures in India, the 6th century BCE, built this great altar. This is what such an altar actually looks like in real life. This is a mathematical abstraction. It's made out of right triangles. There are about 14 different right triangles in this altar, and they're all chosen to have whole number sides obeying what we call the Pythagorean Theorem. And I'll just show you one of them. This is triangle XPD. This is 5, 12, and 13. This big triangle XYC has sides 15, 36, and 39. And this is amazing. So all of this tells us something. First great generalization of the talk. Oh, wait, got something else. I forgot the artists. Artists. Okay, here we have Alberti, Dürer, and Leonardo da Vinci, who developed geometrical methods. And what they're doing it for is to make 2-dimensional pictures look 3-dimensional. Here's Alberti, here's Dürer, here's the most famous example of geometric perspective in Western culture, Leonardo da Vinci's Last Supper. Okay, now the generalization. So learning how mathematics is different in different cultures teaches us about the varieties of mathematical thought. If you're going to teach mathematics, it's really useful to understand that there are many ways of thinking about mathematics. Second, learning who has done mathematics teaches us that mathematics is a universal human activity. You don't have to be a professional mathematician. You don't have to be a white European Christian man. I am grateful to Pitzer College, as I trust all of you are, for its emphasis on multicultural understanding, and also for the way Pitzer gave me, as it did you, the freedom to pursue what we wanted to do. In my case, to study mathematics in many cultures and to have taught it for almost 30 years. All right, here goes the second part of my introduction, a series of generalizations. Mathematics is found, I wrote here, in all cultures, in virtually all cultures, though only in the modern world are there people whose profession it is to do it. Modern mathematics is the product of the work of many cultures and of people from all over the world, as the names of things that we do in mathematics demonstrate. Algebra, that's an Arabic word. Geometry, that's a Greek word. There's a thing in number theory called the Chinese remainder theorem. Okay, point made. Finally, and this is a generalization I want to talk about in the second part of my introduction, A culture develops mathematics that solves a problem of value to that culture. For instance, in Islamic culture, there's a command in the Quran to pray in the direction of Mecca. The Muslims interpreted that as to pray in the direction of the shortest path on the spherical earth to Mecca. That shortest path is the arc of a great circle. A great circle is a circle on the globe that is the same diameter as the whole globe. So if you want to fly from Vancouver to London, you do it by going on the great circle between Vancouver and London. That's what the airplanes do, instead of going on the parallel of latitude, which is a longer distance. So if you're praying in the direction of Mecca, it's not vaguely east. It's 23.85 degrees east of north, as is illustrated on this picture. Teach you an Arabic word, the Qibla, that's the direction of Mecca from wherever it is that you are. Okay, how do you do that? What mathematics do you use? You use spherical trigonometry, which was tremendously advanced in the Islamic world, in order to solve this problem. Anywhere on the globe where you know its latitude and longitude, what's the direction of Mecca? Here's how you do it. This method is due to al-Biruni, great Persian mathematician of the 11th century of the Common Era, 410 in the Islamic calendar. And I think I will leave the details out, but trust me, this works. In our own culture today, it seems to be very important to be able to predict the spread of infectious diseases. So, at the beginning of the pandemic, these graphs were used to explain to the public how to save lives using protective measures to flatten the curve for COVID. I'm actually very glad this particular piece of mathematics was considered important to our culture and people started using it. Here's an example comparing a mathematical model of the epidemic, of the spread of an epidemic, that has actual data to compare the theory to. It's the SIR model that stands for susceptible, infected, recovered. And when you recover, you're immune. This is a model for regular flu. And the little dots are the empirical observations made by the Centers for Disease Control and number of cases and how many weeks into the epidemic. If anybody's interested, I can show you this, or you can screenshot this and study this model in greater detail. Okay, here are the generalizations again. Mathematics found in all culture, even though everybody's not a professional mathematician. Modern mathematics is the product of the work of many cultures, people from all over the world. Culture develops mathematics that solves a problem of value to the culture. That's the end of the introduction. We're now going to move to what I have been calling the really cool example. Just a second, drop my pencil. And here we go. We're going to look at the kinship system of the Malekula people of the Republic of Vanuatu. Where is Vanuatu, you ask? Well, we got a map. If you know where Australia is, you know where New Guinea is, that's where Vanuatu is. It's a small island nation. Here's an enlargement of it. Here's the national flag. I want to talk about the national flag for just a minute because you'll get a little mathematical insight into Vanuatu. You'll notice if you look at all these separate islands, here's the island, here's Malekula, by the way, the culture that I'm going to focus on. One of the islands, you'll notice that the shape is sort of like a Y, letter Y. Well, that's why, WHY, that's why they have this on the screen, on the flag. The colors in the flag, you notice it's symmetric, geometrically top and bottom, but anti-symmetric with the color. This is red, this is green. The green represents the green of the islands, what they look like. The red represents blood for humanity. The black represents the particular people of Malekula. I know all this because the national flag was adopted in 1980. Mr. Malone here is the person who designed the national flag. And let me talk about the other symbolism on the flag. The color of the Y represents the light of the gospel because the population of Vanuatu is about 80% Christian, mostly Protestant. This is the result of missionaries coming to the island, European missionaries. This is a plant called the namele. It grows there. That's what these crossed fronds are like on the flag. And this curved thing is the tusk of a wild boar. They are also native to the islands. So you can see the geometrical abstraction of Vanuatu culture mirrored in the flag. Okay, what we're going to talk about is the kinship system of the Malekula. But first, here's what the islands look like. We want to see the people a little bit. Okay, you got the green part, right? Here are some of the people from the island of Malekula. They're 25,000 population roughly. And by the way, a variety of languages. They don't all speak the same language even. Malekula art is characterized by symmetry and abstraction. That's something it has in common with mathematics. This is a rat, a picture of a rat. This is a banana stump. By the way, they draw things like this banana stump. If you want to see them do it, they can draw it using their finger on the sand. And these designs have the property that you can draw them without lifting your finger and without retracing a line. That's particular. There are results in graph theory that tell you which designs you can do that with. They understand those results. This is a helmet, which I think is charming. Malekula drums are among the world's largest musical instruments. This is an art installation of Malekula drums at the Australian National Gallery. It's a lousy photograph, but I took it. These are some random Malekula drums that I downloaded from the internet. You notice the geometric symmetry, but the anti-symmetry with the color. And I love this picture because first you can see how big the Malekula drums are. And secondly, this man who is playing it is teaching this little kid how to play it. So I think that's just charming. Okay, here we go with the Malekula kinship system. The society is divided into 6 sections. They have their own language for it, but I don't speak any of the Malekula languages. So I'm going to call them the sections 1, 2, 3, 4, 5, and 6. And the society is also divided into 2 halves, right? Here's one half, here's the other half. Okay, what's this diagram mean? Well, first, let's look at the marriage rules. Men in section 1 marry women in section 4. That's what the equal sign means. Men in section 4 marry women in section 1. Got it? Okay, person is in section 2. If he's male, he gets a wife from 5. If she's female, she gets a husband from 5. And likewise, 3 and 6. Okay, everybody got what the equal sign means? Okay, what about the children? Well, the arrows in this diagram, this is a modern diagram that I drew, by the way, so this is not the way they do it. But I drew this modern diagram because this is a very simple way of understanding what's going on. All right, the section of the child is determined by the section of the mother. So if you're in the mother's in section 1, follow the arrow. Children are in section 3, both the male and female children. Or if the mother is in section 4, her children are in section 5. And if the mother is section 5, her children are in section 6. And if the mother is in section 6, back and forth. So you notice that the mother-child relationship for female children, you stay on the same side of these equal sign. Mother, okay, mother, daughter, granddaughter, great-granddaughter, okay? Okay, now suppose we want to work this backwards, and you know what section the child is in, you want to know where the mother is. You do that by following the arrows backwards. So for instance, if a child is in section 3, follow the arrow backwards, the mother is in section 1. Child is in section 5, you follow the arrow backwards, the mother is in section 4. Okay, so now we can find mothers. Next question, how do you find the child's father? Well, let's start with a child in section 3. I want to find the father. The way to do it is first to find the mother. You go backwards. Section 3. Okay, the mother's in section 1. The father is married to the mother. So the father's in section 4. And notice we've jumped over to the other half of the society, to the right-hand half. Father of a child in section 3 is in section 4. Let me ask, where is the father of a child in section 4? Well, here's father in section 4. First, let's find the mother by following the arrow backwards. I see mother's in section 6. She's married to a man in section 3. So the father of a child in section 4 is in section 3. Okay, look what's just happened. Child in section 3, father in section 4. Child in section 4, father in section 3. That is a father-son pair. Likewise, sections 1 and 5 and 2 and 6. A paternal grandfather and his grandson are in the same section. Now, these father-son pairs of sections are important in molecular society. You don't need to memorize this. You don't need to keep track of it, but you just need to be aware of this particular property, that the father of the father is back in the same section. Okay. What about mothers and daughters? Well, a woman and her maternal great-grandmother are in the same section. The mother of the mother of the mother is back in the same section again. Okay, we start here. Mother, 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 back in the same section. Same thing on the other side. By the way, notice the anti-symmetry of these arrows. The arrows go in one direction on the left, other direction on the right. It's a property of this kinship system, and therefore part of the geometric understanding of the molecule, even though this isn't the diagram they use. We'll see their diagram later. Okay, cultural meaning of this particular system of kinship, which is different from our system of parents and siblings and cousins and first cousins and second cousins once removed and all that. This kinship system cycles link people of the past, present, and future together. It goes on forever, as many generations as you want. A number of cultures in the South Pacific have similar kinship systems. For instance, the Warlpiri people of Australia's Northern Territory have a system like that, although it has 8 sections and not 6. As far as I know, the history of these systems is not recorded, but there are conjectures about it. One conjecture is that the original one, and maybe later they copy, other cultures copy this, the original one came from the coming together of 2 peoples. And they said, well, yeah, we'll marry your women, you marry our women. So that's why you have this 2 halves thing. There's also a conjecture that the anti-symmetry of these parent-child relationships gives a greater genetic distance between parents and children, which in a very small society would have survival value. It's a conjecture, because when I ask my anthropologist friends about the origin of these kinship systems, they tell me nobody knows. All right, now we're going to move to the cool mathematics part. We can represent the molecular kinship system rules using algebra. Let's write in the same section as I. Let's designate mother as M. Let's designate father as F. Okay. Well, since the mother of the mother of the mother is back in the same section, we will write mother of the mother of the mother as MMM or M cubed. And since the mother of the mother of the mother is back in the same section, M cubed is equal to I. Likewise, the father of the father, if you'll remember, is back in the same section. So we'll write father of the father as FF or F squared, and F squared is equal to I. That is, father of the father takes you back to the same section. Summarizing, we got M cubed equals I, we got F squared equals I. M is mother, F is father, I is identity. One more algebraic question. When you multiply numbers, order doesn't matter. 3 times 2 is the same as 2 times 3, or xy is the same as yx. So we might expect that mf equals fm. Here's a question. Is mf equal fm true in the molecular kinship algebra system? And the answer is no. The mother of the father, I'm not going to go through the details. I'm just going to tell you. If you want to see this slide again, question period, I'll show it to you. The mother of the father of somebody who's in section 1 is in section 4. The father of the mother of somebody in section 1 is in section 6. Those are different. So in this algebraic system, the mother of the father is not in the same section as the father of the mother, and therefore MF is not equal to FM. For the math people, this is non-commutative. For the non-math people, they're just not the same. Okay, it turns out that the father of the mother is in the same section as the mother of the father. And again, I don't want to go through the details for you. Will you? I hope you'll trust me on this. Always true. Father of the mother and mother of the mother, father are the same. Okay, now that we understand the algebra for the molecular kinship system, I want you to do two things. I want you to forget all about my modern diagram with the arrows, because we've translated it into this algebra. These equations give you the whole story. But second, I want you to come along with me, and we're going to look at another piece of mathematics that is different, that is simple, that's very, very cool in its own right, because afterwards, this new mathematics will help us understand the molecular mathematical representation of their own kinship system. Let's see how that happens. All right, what we got here is an equilateral triangle. It's got 3 equal sides and 3 equal angles, and I have labeled them the angles A, B, and C so we can keep track of them. What are all the things we could do to this triangle so that it still looks the same? So that it's got a point on the top and the base is parallel to the bottom of the screen. Those things are called the symmetries of the equilateral triangle. Well, one thing we can do is just leave it where it is. Let's call it leave it in the original position. Let's designate leave it in the original position as I for identity. That's not a very interesting one, but that is a symmetry. Okay, next. Another thing we could do is rotate the triangle until another side is parallel to the bottom of the screen. Let's take the original triangle and rotate it counterclockwise so that the B goes up to the top where the A is, and the A goes down to where the C was, and so on. It'll look like this, rotated 120 degrees counterclockwise. And I've decided to call that rotation M as in mother. Okay? Those of you who understand group theory already know where I'm going, but the rest of you, hang in. Let's do it again. Let's rotate it another 120 degrees counterclockwise. One rotation was M, 2 rotations. Okay, here's M. Now we'll rotate it again. Now the C is going to be on top. So MM, or M squared, looks like this with the C on top. What happens when we rotate it yet again? So we rotate it counterclockwise 3 times. Well, we're going to get back where we started. The first time, that puts the B on the top. The second rotation, that puts the C on the top. Now we rotate it 120 degrees again. There's the A on the top. So look, 3 rotations aren't a new symmetry. They're the original I we had. So M equals M cubed equals I. I trust you recognize this equation. What else can we do with this geometry? Well, we can flip the triangle over the vertical axis, yeah, like that. So we see the triangle's back. Let's call that flip F. That's a good thing to call a flip. So you see the A stays on the top, but the B and the C change places, and we're looking at the back of the triangle, which I have in a different color here so you can keep track. That's what we did. So that flip is F. Now let's do that again. Flip it twice. When we flip it twice, we get back to the original position again. Flip once looks like this, flip it again, A is still at the top, the B and the C are back where they were. So we have FF equals F squared equals I. Are there any other things we could do to make the triangle look the same? Well, we can do the rotation and then flip. Rotate it 120 degrees counterclockwise, so the B's up on the top, and then flip it over the vertical, so it looks like that. The B is still on the top, but the A and the C have changed places. This is a new one. Well, it's rotate and flip, so it's MF. Another thing we could do is rotate it 120 degrees counterclockwise twice, and then flip it over the vertical. Okay, rotate it once, get the B on the top, rotate it again, get the C on the top, now flip it. So now we have C on the top, but the A and the B are not where they were before we did the flip. So this one is rotate, rotate, flip, M, F, or M squared F. And that's it. That's all the symmetries of the equilateral triangle there are. Here they are. I, leave it alone, M, rotate it once, rotate it twice. Flip, rotate and flip, rotate twice and flip. And as we've seen, M cubed is I and F squared is I. This algebraic structure looks very much like the algebra of the kinship system, but we do want to ask, for the symmetries of the equilateral triangle. Is MF the same as FM or not? What do you think? Answer is no. Here's MF. First, we rotate it 120 degrees counterclockwise, then we flip it. Notice the B's on the top. Here's FM. First, we flip it over the vertical, then we rotate it 120 degrees counterclockwise. Now the C's on the top. So MF is not equal to FM, but FM is not a new symmetry because FM, just as for the molecular kinship system, turns out to be M squared F. Here's M squared F. Rotate once, rotate twice, flip. Here's FM. First flip, then rotate. Again, C on the top, the A and the B on the bottom in the correct order. So summarizing what we've done so far. First, as we saw, the modern arrow diagram I used for the kinship system, that represented the kinship system of the molecula. Second, we saw a modern algebraic structure for the kinship system. Third, we saw a geometric analog to that algebraic structure, namely all these symmetries of the equilateral triangle. Okay, from the mathematical point of view, the thing that surely has struck all of you, all three of these representations have exactly the same structure, even though they are three different representations. The first one was geometric that I wrote. The second was algebraic that I wrote. The third was geometric, that the equilateral property that equilateral triangles have always had. All the same structure. But the culturally interesting question is, how do the molecula themselves represent their kinship system? And before I show you that, let me remind you of all the things we saw about molecular culture, the interest they have in diagrams, the interest they have in cycles, the recognition they have of symmetry and anti-symmetry, and of course the properties of their kinship system. All these things are going to be packed in to whatever it is that they do to represent their kinship system. Culturally, they have names for the sections, not numbers. Varied relationships play key roles in their society, but today we're concentrating on their mathematics. And so what we want to know is this. How does a molecular person answer questions like, hey, in what section is the mother of the father of the mother of your father? That's the kind of question that might come up. They do it with this diagram. Okay, and before I talk to you about how the diagram works, I want to point to some properties of the diagram and see that it has threefold symmetry, like starting with these three arrows, okay, like the triangle rotations, right? It has twofold symmetry. Look at the circles. There are two sets of outer circle, inner circle. It has anti-symmetries to see how the arrows go in one direction and on the outer circle and the other direction on the inner circle. So I hope it's at least plausible to you that their diagram is capable of containing all the information that our modern representations contain. But you look at it, you say, my first reaction, first time I saw it, what? We need help to understand it. Now, if there were molecular people here, what they would do, because this is how they explained it to the anthropologist Bernard Deacon, who wrote about it, they would construct the diagram for us step by step, explaining their kin relationships. They would start with a diagram by which they represent the three father-son pairs, which is just these arrows. And then they would add joined pairs of lines, a long line for male and a short one for female, to represent the men's marriages, okay? So here is a man and a woman being married. Here is a man and a woman being married. Here is a man and a woman being married. And then a set of lines closer to the center of the diagram, like this one, to represent the male and female children and the sections where they were from. And then they would add arrows to show you the marriages in both directions. Remember, men in section 1 marry women in section 4. Men in section 4 marry women in section 1, and that's why the arrows are going in different directions. But you can see here is the marriage we looked at before. Here is the marriage in the other direction, where the woman is from elsewhere and the father is from elsewhere. And this is the completed molecular diagram. But if you still don't get it, which I think probably you don't, Marcia Asher, who wrote a book about ethnomathematics, the mathematics of traditional peoples, has redrawn this diagram with modern algebraic labels, showing us clueless modern people how their diagram in fact represents their kinship system. So if you start with I, the section that you were in, here's your father and here is your mother, represented getting married, and all the other marriages, permitted marriages, like if you're an I, you marry somebody in the section of the mother of your father. If you are in the section of your mother's, if someone is in the section of your mother's mother, that person marries somebody from this section, and so on. But for our purposes today, we don't need to learn how to use the diagram, the molecular diagram in detail. What we do need to do is respect it, because it does the job for them. Here's what the molecula have done. They have abstracted a concept from the world of their life experience. Then they have embodied that concept in a mathematical model. Okay, when I did that, I did an algebraic model. They've got a geometric model, but it is mathematics, it is a mathematical model. And they then reason about the structure of that mathematical model, of that mathematical object. They reason about its symmetries, about its cycles, and they do it in order to answer questions about the real world situation that is modeled by that mathematical system. So the molecula, like our modern epidemiologists with their graphs, like the medieval Muslims determining the direction of Mecca by spherical trigonometry, the molecula have developed their own mathematical procedures and have used them to solve a problem of importance to their culture. Let me say that again. The molecula, like modern epidemiologists with their graphs, medieval Muslims using spherical trigonometry to find the direction of Mecca, the molecula have developed their own mathematical procedures and have used them to solve a problem of importance to their culture. I hope that this has helped you appreciate these generalizations. All cultures have some kind of mathematics. Cultures develop mathematics that solve problems that they think are important. And number 3, mathematics is an essential human activity. All peoples have created it, and it belongs to all people. A Pitzer student once wrote on one of my teaching evaluations, "I appreciated seeing how people who are like me have contributed to mathematics." I think everyone, not just the student, everyone should have the chance to appreciate this, because mathematics belongs to us all. Okay, for today's talk, I particularly want to express my appreciation to these researchers, Marcia Asher, who wrote this book, Ethnomathematics, A Multicultural View of Mathematical Ideas, and Bernard Deacon, the young anthropologist who studied the molecula, and Victor Katz, who literally wrote the book on the history of mathematics. I wanted to give you some recommended readings if you're interested in pursuing some of these topics a little bit more. Marcia Asher's book that I just mentioned. The name ethnomathematics chosen by the Brazilian researcher Ubertan D'Ambrosio, he named the field, and Marcia Asher literally wrote the book on it. Joseph, who is of Indian origin, that is from India, wrote a book called The Crest of the Peacock, Non-European Roots of Mathematics, which I recommend particularly for its account of Indian, Chinese, and Islamic mathematics, and a piece of mine on how to teach a course about mathematics for non-mathematicians, which among other things talks about my Math in Many Cultures course and actually quotes a number of Pitzer students in it. Okay, so questions, this is the time for questions, which you can ask now in the chat, or you can email me later if you don't have them, but I am going to hit escape. So if someone has a question in the chat, they can ask me one. And if nobody has a question in the chat, I can tell you, I will answer the questions I get most often about this kind of stuff. So. All right. Are there any other cool examples of culturally relevant problems? Gee, I don't know where to start. The Egyptians, one of the really cool things the ancient Egyptians did was using their number system, which is very cumbersome. They solved the accounting problem of building the pyramids, which, I mean, there are tens of thousands of workers involved, and just the number of onions that had to be cataloged and so on. Plus, they learned the geometry of pyramids. And there is a quotation from a historian of mathematics called Eric Temple Bell, who said, the greatest Egyptian pyramid was the one in the mind of the anonymous Egyptian writer who found the correct volume formula for the frustum of a pyramid. That's a pyramid with the top cut off. So I think that's a good that's a good example. The first time I talked about this stuff, Stuart, is I gave the example in modern culture of a problem that is, if you have a moving projectile and you have another projectile that is tracking it and wants to catch it, okay, that's a problem of interest in our culture. That's how an anti-missile shoots down. But I like the epidemic example better. The problem of designing an altar for religious purposes with proportions that mirror the cosmic order, that problem has been solved by many religious figures in many cultures. And just to give you an example from the Bible, you read about the construction of Solomon's temple. It's all full of numbers. There's something going on there. The cosmic order, God expresses himself with numbers. God counts the days of the week. God determines that the seventh day is the Sabbath. Okay, these numbers all have all kinds of meaning. I mean, I could go on, but there are lots. And I commend to you this. Well, all right. I don't have the slide anymore because I stopped sharing the screen. But I have Marcia Asher's book. Okay, so you see the pattern there on it. That's that there. See the colors and the curved symmetries. That's a Maori diagram. It's a rafter pattern, and what's going on? What the Maori are doing is they're making strips that represent different symmetries, and they've got all the different symmetries for strip patterns in their rafter patterns. And if you ever are fortunate enough to go to the Alhambra in Spain, the Islamic geometric patterns there give you all kinds of geometric symmetries. They thought that the Muslim architects, they thought that symmetries, geometric symmetries, reflected the unity of God and the variety of manifestations. And I've got a book here, which I'm actually glad I had it on my shelf. It's Geometric Patterns in Islamic Art and Architecture. It's all kinds of mathematics. I mean, I mean, there are millions of other examples, literally. Okay. Lisa Zucker, send me an email and I'll send you the teaching company website, or you can just Google the teaching company, because you don't need to know anything anymore. You should just type it into the Google search field. But if you can't find it yourself, I'll be happy not only to send you the teaching company website, I'll send you the specific website for my course if you want.
Judy, is that actually what it's called? It's actually called the teaching company website?
It's called the teaching company.
Okay, thank you. I was also asking.
Yeah, okay, no, sure. Okay. Another question that, since nobody else has asked one, another question that people ask me all the time is, should we keep calling it the Pythagorean Theorem, since it looks like they had it in India? And by the way, they also had it in China. And we don't have texts that show they had it in ancient Egypt, but I wouldn't be the least bit surprised if they found a text tomorrow, because you really can't build pyramids without discovering the Pythagorean Theorem. And, there's lots of things like that. So when people ask me that, things get named after whoever puts them into circulation at the time textbooks are being written. And if you want an example of something that is named after a person who A, did not discover it, and B, did not create it, consider the continent that we live on.
I know, I was going to say Columbus.
Well, no, not Columbus. It's Amerigo Vespucci. The continent's named after him. Okay, well, okay, but literally he put it on the map, and that's why it's named after him. Okay, here's another question. I remember there is a traditional assignment of numbers to Hebrew letters. Yes, the Hebrew alphabet, before the Hebrews learned about numbers from the Arabs, they used their alphabet just the way the Greeks did, okay? And the example that Stuart's question has is that Chai, which is the Hebrew word for life, is Chet, which is the 8th letter, and Yud, which is the 10th letter. And when you add 8 and 10, you get 18. Okay, they don't have a tally system, so you just have to know that 10 plus 8 is 18. By the way, the number 18 also tells you that it's 8 plus 10, but alphabetic numbers don't do that. But what they do give you is tremendous cultural push in that if two people are getting married and their names, their Hebrew names, happen to have the same numerical value, believe me, whoever is performing the ceremony will talk about it at great length. And the computational system that people use when they have an alphabetic number system, if you're going to do any complicated computations, the alphabet is not going to help you one single bit. So it's good to have a counting board, which people invented. Let me give you another example, by the way, of culture and numbers from our own society, which I think is kind of interesting. So all the numbers on your screen, the thing that tells you how many participants there are, the thing that tells you the date, the thing that tells you the time, we're all using the Hindu-Arabic numerals. But when they make a building and they put a cornerstone in it saying when it was built, or when they're telling us which Super Bowl it is, they use Roman numerals. And those things have cultural meaning to us. I mean, even if it's just to get you to say those football players are like the ancient gladiators, it makes a cultural point. And so you also see in religion discussions of why things are a certain number, and the lucky numbers in different societies are different. Okay, I find that actually fascinating when somebody tells me that 13 is not an unlucky number in their culture. Well, okay, yeah, fine. There's something about numbers that grabs people's imagination, because numbers, in a sense, are like God. They are unchangeable. 2 and 2 is always 4. Winston Smith says in 1984, the novel, freedom is the freedom to say that twice 2 is 4. Once this is granted, then all else follows. And mathematics gave a model of truth. And it was something that even Big Brother shouldn't be able to talked you out of. And I think that the kind of mystical things in religion that about numbers are related to numbers having that property. So, more question? I also think it's still okay to call it the Pascal Triangle, but in my Math and Many Cultures course, we called it the Meroprastara from the Hindu name because Halyuda, as far as I know, was the earliest person to have it. And it's not really known whether any of these other cultures who had it influenced 17th century mathematics in Europe, where Pascal. So it's all right. It's all right if you're talking about probability theory to attribute it to Pascal. But I hope you come out of this understanding that significant mathematics is developed by a wide variety of cultures, and that therefore, whoever you are, male, female, white, black, straight, gay, Christian, Jewish, Muslim, whatever religion is followed by anybody, anywhere, can all do mathematics if somebody's just had the decency to do a good job teaching it to you. Okay? Are we out of time or?
Well, we don't want it to end, but yes, we are almost to the end of our time, Judy.
Okay, I guess I want to say one more thing on behalf of my, this is a mixed metaphor, my fellow women in the world. Okay, in the year 1900, the percentage of women getting PhDs in mathematics in the United States was 0. Now it's in the 30s. This is not a biological change. And so for those of you who are women or who know women or who have female children or know little kids who are girls, they should be aware that this is something that they can do. The first woman we know about in the history of mathematics was Hypatia of Alexandria, who lived in about 400 and came to an untimely end because she was also a philosopher, and the religious authorities in Alexandria did not like what she was doing, and it's not a pleasant story. She got killed. There are a handful of known women mathematicians really until modern times. What changed? Higher education. Because mathematics is not the sort of thing that most people can teach to them. Well, elementary mathematics, maybe you can teach to yourself, but if you want to make contributions to the subject, you need higher education. Let people into higher education, and all of a sudden you discover, hey, these people can do it too. That is, by the way, also, that applies not just to women, but to any group of people that has been barred from access to higher education. So if you're teaching mathematics to anybody, including to some little kid in your family, mathematics belongs to everybody. Anybody can do it. The Maya had a place value system based on 20 instead of 10. They invented the 0. There's nothing anywhere here that any group of people is not capable of learning. So, okay, well, Lee, thank you guys for coming, and all power to Pitzer College for having enabled me to learn this stuff.
Thank you so much. This was amazing. I just get so excited. Thank you.
Well, thank you.
Thank
Okay,
you,
guys,
Judy.
thank you. Okay, you guys have my email if you have further questions.
Thank you, Judy. It was
Yes.
great.
Thank you.
Miss
It was great to see you. It was great to see you. Well, thanks everybody who's writing all these.
Thank you.
Thank you.
Yes.
Thank you.
It was really wonderful.